All right, welcome everyone to the Cartesian Cafe. We're very lucky to have Alex Kontorovich here with us today. Alex is a professor of mathematics at Rutgers University and served as the distinguished professor for the Public Dissemination of Mathematics at the National Museum of Mathematics. Alex has received numerous awards for his illustrious mathematical career, including the Levi L. Conant Prize in 2013 for mathematical exposition, a Simons Foundation Fellowship, an NSF Career Award, and being elected Fellow of the American Mathematical Society in 2017. He currently serves on the Scientific Advisory Board of Quanta magazine and as editor-in-chief of the Journal of Experimental Mathematics. Welcome, Alex. How are you doing today?
I'm doing well. Thanks for bringing me on here, Tim.
Great. Yeah, great to have you. I just wanted to start out by asking a little bit more about your experience as a mathematician. I see you're quite involved in a variety of things. Insofar as a mathematician is involved in many different areas of mathematics. You're a pure research mathematician. You also, I guess, at least oversee experimental mathematics. I don't know to what extent you participate in it. And also more recently, you're involved in formal theorem proving. So those are quite different areas of mathematics that very few people are involved in all three. Can you kind of explain how you ended up wearing so many hats? Do you wear one hat per day or multiple hats per day? How do you juggle those?
That's a great question. It's funny because coming up through the ranks of, school math to college to grad school to postdoc to tenure track, I think I was always just wanted to stay out of anything that's not proving a theorem. And just wanted to spend all of my time devoted to theorem proving and doing nothing else. And I sort of got into the outreach side of things by accident, in the sense that, you mentioned this career award that's an NSF thing, and unlike a standard NSF grant where you just say, these are the theorems I hope to prove over the next couple of years. And I'll do some, broader impacts because this is why Congress is giving it to us. How are theorems going to help society? And the God's honest truth is, well, they probably won't for the next century. But 90% of them, or 95 or 99% of them, won't ever help society. But there's 1%. There's that a bunch of theorems that humanity, for whatever reason, decided they were going to think about. And then it ended up having profound impacts on the world as we know it. So stupid things about prime numbers that nobody cared about except for number theorists ended up enabling exactly the communication that we're having right now. Questions that as a kid I would have found just absolutely asinine about whether you can prove the parallel postulate from the other four in Euclid's axioms of geometry. Who the hell cares? Let's just do some math. And that ends up explaining Einstein's general theory of relativity is the mathematical tools were in place for Einstein to be able to use them to understand the nature of space-time. So those are some examples that we say to the NSF, and the NSF politely says, okay, fine, here's some money, but they want to see some broader impacts. And for a career grant, they want a more in-depth outreach component or educational component. There are people that go build schools in Venezuela or something, and go give lectures in India to mathematicians. And so I was teaching at Yale at the time, and we had already a monthly lecture series for New Haven area kids, and so I said something in my proposal I'll give one of these a year over the next 5 years. So please, can I have the grant? And when I got the reviews back, it was funny. I haven't looked at them recently, but it was something like, well, we'll give you the grant, but your broader impacts are crap, and you better do better than what you said you would do. But we'll give you the grant anyway. So I got the grant. So I sort of didn't learn my lesson. For the first couple of years, that's what I did. I gave my one lecture a year on whatever it was to the local area kids, which wasn't nothing. But and I should say, I do really enjoy lecturing. When I said I just want to do theorems, I do just want to do theorems, but I always found it impactful to be able to like I love theorems and I want other people to love theorems. And so I took my teaching very seriously. I didn't spend a lot of time on it, but I feel like I'm a conscientious instructor. Like I really want the students in my class to know the subject and to understand why we're doing what we're doing and to enjoy it. So I do like lecturing, and I enjoy that component of it. And I did this, little dinky outreach thing. And then in the middle of that grant, I moved from Yale to Rutgers. And so I had to do something for my broader impact component. And so I asked around, well, do we have one of these, lecture series that I could just plug into and not have to do any actual work? And it didn't seem like there was such a thing. But just around that time, the MoMath had opened up in New York City, which is, a hop, skip, and jump away. Actually, at the time, I was still living in New York City. So it was even easier. So I just wrote to them and said, I'm a mathematician. I just moved to Rutgers. Maybe I can come give a talk. I have this NSF grant I'm supposed to do something with. And they said, who the hell are you? And then we continued communicating over some period of time. I had given some other talk that they attended, to check it out. And they said, okay, fine, let's have you come in and give one of these. It's called Math Encounters, is their sort of flagship program where they bring in math professors to give a talk to the public. So that went well. And then a year later, I gave another kind of thing. And then sort of very slowly over time, I got more and more into the role in the mission. I mean, I was always on board with the mission. I think we do an absolutely horrific job of explaining what mathematics is all about. Not even what mathematics is, just like what is the goal of mathematics. The fact that there exist human beings who think about math theorems for a living is news to 95% of our 99%, whatever, of our fellow citizens. So that seemed to me like a really worthwhile thing. And I always kept it, I'd like to think I still do keep it on the sidelines, and theorems are still my first love and my first priority. But I'm getting more and more as over time, I'm getting really more and more meaning out of the work that I do in the outreach space. I still love my theorems that 5 people in the world will appreciate. There's no taking that away. But being able to reach, especially so during this year that I was this distinguished visiting professor there, I started doing a lot more outreach, especially with YouTube, because that's a resource that I think is a complete game changer in terms of, especially now in the COVID era, if everybody's just posting there. I'm doing the same thing. I'm just posting all my lectures. Anytime I give a lecture, it's going online. Anyone around the world can have access to the same lectures that it used to be. You had to drive down to Princeton or something to hear whatever the top people were thinking about in these days. And now you can be anywhere in the world, and you can zoom into the Princeton lecture series, or the Rutgers lecture series is online, and so on. So I think we're entering an era where people will be able to communicate across. There's a whole lot more information that is very readily available to people than ever was before, and I think it'll have profound effects on society. I hope in good directions and not bad, because that is not obvious. Anyway, so the outreach work became more and more meaningful, and then at some point Quanta asked me to come on board, and so I enjoyed that part of it. You had asked about theorem proving. That's a much more recent addition to my interest, but I don't see that as separate from my standard math work, in the sense that a lot of the time, so I work in analytic number theory, and a lot of my papers will be 40, 60, 100 pages of extremely difficult, tedious, long computations. And in order for me to even begin to work on them, what I usually have to do, maybe I learned this from working with Jean Bergan, my collaborator on many of these projects. He always stayed up until 4 or 5 in the morning. I would work with him until 1 or 2, and then I would get on the last train home. And by the time I got home at 3 or 4 in the morning, I'd have another email from him, following up on what we had been discussing for the last 6 hours. So I realized that just to get started on a project, just to load all of the data into my brain's RAM takes a good 2-3 hours, and I have to like lay out the papers on a big desk where everything's in place. And then, I want to, once it's loaded, I want to have a good 4 or 5 hours to actually work on it. And I realized the only time I can do that is between 10 p.m. and 6 a.m. And so that sort of became my modus operandi. This was around the time that we just started having kids anyway. So I was up throughout the night as it was. And it was very convenient. I would, we would do a feeding at like 9 o'clock, and my wife would go to bed. And then I would just stay up and work and do this thing. And then the baby'd wake up at midnight. I'd give him a bottle. I'd put him back to bed. Wake up again at 3. I give him another bottle. And then by 6, I'm wiped. But I've had those basically uninterrupted hours. There's no email coming in. There's no, like, if I want to take a break and I want to see what's on it, there's nothing on the news, right? There's like nothing that can distract me. As much as I try to distract myself, there's nothing going on. And so I have no other choice but to continue working. And so for God knows how long, that's basically, one or two nights a week is like that. And so, so when I saw Lean, what I really saw was, oh my God, maybe I don't have to do this anymore. Maybe I can have, eventually, we're still very far from this because it's nowhere near the point where I would actually be able to prove any of my theorems formally. There's just too much that needs to be built before that becomes a reality. But if it eventually does, how amazing would it be to be able to just open up the computer, and the computer is taking care of the RAM, and I can go straight to the next issue that I need to deal with. And I can, so I really appreciated what Lean was doing in terms of just being able to store very, very complicated proofs and keep track of things in a way that I didn't have to do it myself. And it's rather similar, I think, to this liquid tensor experiment that Lean just carried out, where Schulze had a theorem that was, very complicated, and he wanted people to check it. I mean, I am pretty sure I've given enough talks and lectured to, not just talks where you talk about things, but graduate courses where my graduate students have gone through with a fine-tooth comb everything that I've done. And so I haven't found any mistakes yet. But so I'm not worried about mistakes. I'm just I see it as a tool. And really what I felt when I first saw this is fear that some young kid is going to know how to use this and I won't, and they'll just mop the floor with me. And so this is me trying to stay with the kids,
I see.
Stay up on the latest tools.
I see. Actually, in preparation for our conversation, I listened to your other podcasts you've been on, Steven Strogatz and 3 Blue 1 Brown, and maybe that gets the segue to one interesting question I had about something you said about your experience with Bourgain and collaborating with him, and one of the ways in which you coped with that was you said that you're not competitive, or somehow that allowed you to cope with that. What you just said, I'm just curious how that contrasts with what you just said in terms of the kids displacing you. So I used to be an academic, and then things didn't work out for me, and in contrast to your non-competitiveness, I always felt that to kind of, to succeed in academia, since there's so few positions and since it's it's zero sum, there's only a finite number of universities, a finite number of positions, they're not growing. You do have to have some kind of competitiveness to, I feel like, succeed. And I'm wondering to what extent, like, maybe you were always successful, so you didn't need to be competitive, or maybe it didn't matter. You do math anyways, whether or not you succeeded. I don't know. I'm just I just wanted to kind of dig a little bit about your non-competitiveness and how that's worked out for you.
Yeah, that's a good question. I guess I have to say I was in a very lucky position where I never really thought about the next step very much. I always just wanted to work on whatever it was I was doing at the time. Like, now that I have kids and I'm sort of, we have plenty of time before they go to college, but I'm sort of thinking, like, what the hell did I do in high school? I didn't think about college. I wanted to play music and learn math and do a bunch of, kid things. And then senior year came around and I was like, oh, I guess I better apply somewhere or something. Right. That was like, I'm basically oblivious to the outside world for a long, long time. And maybe now I can look back and start to think. I was always competitive with theorems. Like it's, as Erdos likes to say, there's I don't know if was Erdos an atheist. He's like, God, you don't have to believe in God, but you have to believe in the book. Right?
Oh, okay.
And there's this competition between him and the book, and God won't let him see the book, and he's like desperately wants to defeat God in that and get some beautiful juicy proof. And every time he gets one, he's like, ha, I got it from you. I got one over you. So in that sense, I was always competitive, that I wanted to work really hard and prove a theorem and learn something. But if someone else proved a theorem, I would be delighted. Oh, so how do you do it? Because I've been trying to do this for 5 years or something, and I didn't know how to do it. And I tried this and that and the other. Oh, that was the idea. Oh, awesome. Like I learned something new. It was never, oh no, this guy beat me to it. This girl beat me to it. It was always, I just want to learn. And so that was kind of the competitive side for me. And the other stuff, just, I didn't really, again, I'm sure I was extremely naive, as you said. Now that I have graduate students and undergraduates applying to, however many undergraduates apply to very few positions in graduate school, however many graduate students apply to, I think as a country graduate something like 1,000 PhDs a year, roughly. I don't know if that's ballpark. There's maybe 300 postdocs in the country. And then those 300 postdocs will apply to 100 tenure track jobs. So as you said, there is this very, very sort of steep culling that people should be aware of, for sure, if they want to enter the business. Yes, it is extremely competitive. I never knew any of that as a graduate student or as a postdoc. I just applied and hoped for the best and never thought about plan B. And I knew lots of people who did the same thing and it didn't work out for them, and plan B just kind of worked out anyway, and they were very happy. So I that's the thing, math. Like, I think it really is true that math, having skill at math is the reason we love abstraction, is because it can apply in so many different situations. And I think it really is not just lip service that we tell students, oh, it's important to study math because you'll have basic skills that you can apply to anything. It's actually really true. And it seems to be the case that the market sort of rewards people with significant skills in this direction. And so I never felt competitive or worried about my next job. I got really lucky, and they came when I needed them. I don't know if that answers your question.
No, sure. Yeah, actually, one other, maybe to wrap this part up. But actually, you said one thing that I thought was very nice, which was that, supposing, say, math didn't even work out for you, it's just you love math and you do it anyways, even if someone wasn't going to pay you to do it, right? And in some sense, that's what I'm doing now, what we're doing right now, which is that, like, okay, I'm not a research mathematician anymore by title, at least, and I don't therefore have the much time to do research mathematics. I mean, I'm an AI researcher now, but that's not the same thing as mathematics. But nevertheless, since I do like math, I now have this podcast, and I'm just doing it for fun anyways, right? So I could sort of resonate with what you just said there, and it's great to also have people like you also who want to just talk about math. It's great.
Yeah, for sure. I mean, I'd like to say that no matter what, I would still be doing research, no matter what job I had during the day. I don't know if that's actually realistic. Maybe if I had a job where I really had to do something other than think about math, I'm sure then in a couple of years, I would no longer think about math. I mean, it would be very difficult. It's like playing an instrument and then putting it down for a couple of years and then, go play a gig. I'll need a couple of weeks to get my chops back up to be able to shed the material. But so far, I have tenure, so that's it. It's worked out to the point where you're absolutely right. Like I don't have a job. I just do what I would be doing if I was like infinitely rich and didn't have to think about money. Well, basically that is the situation, right? Like I don't think, like as far as I'm concerned, like I tell my kids are like, who's the richest man in the world? And I'm like, I am. Like, what do you mean you are? There's Bill Gates, there's Elon Musk. Like, no, I wouldn't. How much? What would I trade my life for? $1 trillion, maybe. I don't know. I don't know that would get. I don't know that $1 trillion. If I had to give up my family and my theorems and my lifestyle, would I trade it for $1 trillion? No, that means I'm worth more than $1 trillion, and that's more than I'm told Elon Musk is worth. So, every value is subjective. So every single person can be the richest man on the planet, man or woman on the planet. So that's sort of how I feel, and math has allowed me to feel that way. And obviously, that's a huge privilege, but I've been very lucky.
Wow, that's a very fascinating way to think about things. That's way out of scope for what we're going to talk about today. But that's because money is like an objective number that you can attach, right? Wealth. But this richness that you're talking about, it's like everyone can think. In an ideal world, everyone would be the richest person in his or her own mind, and then that'd be fine, right?
Yeah.
I mean, we don't live in that world, but it would be, it's somehow theoretically possible if everyone were just maximally happy with respect to their own metric.
Right. I mean, that's the fact that value is in the eye of the beholder is precisely what makes the market work, right? I want a tomato more than I want my dollar, and the grocer wants my dollar more than he wants a tomato. So there's that imbalance, which is how wealth is created, right? So if people think of things that way, then they'll realize everyone can be the richest person in the world.
Indeed, and unfortunately today we have the right trade-off between time and talking about math. So why don't we jump into it? So Alex, we did talk a little bit today or previously about what you might talk about, but you kind of wanted to leave it a little bit of a surprise. So usually with my podcast, I do a fair amount of preparation. I usually start being in the driver's seat and putting an outline. But in this case, I'm going to hand it off to you to be in the driver's seat. So what are we going to talk about?
Yeah. Well, the kind of math that I was always drawn to, it's funny. There are certain personalities. There are people who someone just says, okay, a Lie group is a manifold with a group structure, and these are the axioms, and let's start go. And I never liked that kind of math. I always liked math that was like, here's a puzzle. Here's a very concrete thing that, like, how would you not? Here's a pattern. Here's something funny. Can we understand it? Then if you have to go and develop some big heavy machinery, I'm perfectly happy to develop heavy machinery if I know if the thing that I'm trying to do with that machinery is something that speaks to me. And so the kinds of problems that I think a lot of number theorists feel this way, actually. Maybe that's why we become number theorists, is we like problems that you can explain to a child, but they take significant investment to be able to make progress on, if not answer outright. So the kinds of things that I thought we could talk about today are some work I've been doing over the last God knows how many years on sphere packings that starts in extremely elementary directions. And that's why I said you don't have to prepare anything. It really is something that I don't know if it should be taught in 8th grade, but it certainly could be taught in 8th grade. But isn't, or at least I didn't learn it in 8th grade. And I'm this is my chance to get back at my, I don't know, my teachers or something for not telling me this stuff in 8th grade, making me wait until I was a, grad student or postdoc or even beyond to learn some of these things. But so let's start, there's a couple of directions of the beginning, but we can sort of go all the way back. So here's a problem that Apollonius of Perga, an ancient Greek mathematician, this was like all the rage in 300 BC. So, as you said, I'll be in the driver's seat, but I think it's better if you draw, because then whatever I say, at least one person has understood.
Sure.
So if you draw three, okay, let's do it like this. Draw for me, please, a 3, 4, 5 right triangle.
Oh,
so 3,
okay,
4,
let's
5
do it.
right triangle.
I think I can still do this. I haven't done it in a long time, but okay, let's do it. Okay, so
to the best of your
maybe
drawing.
Okay, that might be a little bit too isosceles, but let's just pretend it's 3, 4, 5.
Okay.
Okay.
And a 3, 4, 5 triangle is actually you see the 3, the corner where the 3 and the 5 meet. Let's call that point A or something. And where the 4 and the 5 meet, let's call that B, and the right angle we'll call C. Okay, so if I draw a circle of radius 1 centered at A.
Okay, let me use maybe a different color now. Okay, so circle of radius 1, so I don't know, something like that.
Perfect. And if I draw a circle of radius 2 centered at C.
Okay, so they better touch. Yeah, so they better be tangent.
Exactly right.
Okay, and they better go roughly halfway there. Okay.
Let's see. Am I going to get this right or not? No, it looks like I'm not getting it right. If you draw a circle of radius 1, of radius 2, and radius 3 in a way that they're tangent.
Well, let's see.
Here, let me draw it off to this.
Do you want to draw the third? I don't know where to put this one.
1, 2,
I see.
And then 3. So the point is that this distance is 1 plus 2. This distance is 1 plus 3. And this distance, okay, so at C should have been radius 1. That's my mistake. So just pretend that this circle that you drew here is radius 1. Okay, so you see how a 1 circle and a 2 circle and a 3 circle turn into a side of 3, a side of 4, and a hypotenuse of 3 plus 2 is 5.
Okay, so let's just draw these numbers: 2, 2, 3, 3, 1, 1. Right?
Perfect. Okay, great. So here's your exercise. This is the kind of thing that Apollonius would say. Draw with straight edge and compass a circle that's tangent to the 3 that are given here and work out its radius.
Well, off the top of my head, I don't know what that radius is. I don't know if I should, right? I mean, I don't know. Okay.
Nope, there's no reason to know what that radius is. In fact, Apollonius didn't even really ask for the radius. It's much later that people started thinking about the relationship between the radii. But the drawing of that 4th circle with straight edge and compass, that was the Apollonian problem. Now,
oh, I see. Okay, find an algorithm to do that.
Yes, exactly. Find a construction algorithm to do that.
So, are you asking me to come up with that algorithm right now?
I would be. It's extraordinarily difficult.
Okay.
So
I'm trying to think about it in terms of like, okay, like I haven't used a compass or whatever in a long time. So it would like, what would I do and then translate it into the compass method? Let's see, like, like I kind of naively, I think in my mind, what the first thing I might try is like, can I find where the center is? And then you just kind of expand the radius until it's tangent to all of them. And then see if you could convert that to a compass method. But that's absolutely like my intuition. Yeah.
Yeah, absolutely. That's good intuition. The hard part is certainly finding that center, because once you know what the center is, you just draw a straight line to each of the
exactly. Yeah.
And then you know where it intersects, and then there's your 3 points. So yeah, finding the center is definitely the hard part. So let me give you a solution to this, which I call Viette's solution, but that's probably not historically accurate. But it has to do with circle inversions. So this is something that the Greeks had. They wouldn't have thought of it as transformations and inversions, but they had all of the mathematical know-how to be able to execute it.
Oh, I see. Okay. Now that you said inversion, I know what the solution is.
Okay, so tell me the solution.
Okay, well, basically, there's this inversion transformation, which we'll describe in a second. Basically, you
So I'm just going to draw 3 other circles off to the side here. So now we have a fresh picture.
Yeah. So basically, if you invert through a circle, what you're doing is, you basically put the origin at the center and just basically take the reciprocal of the radius in polar coordinates. Right.
Beautiful.
Right. Okay. So the inside becomes the outside, and the boundary of the circle remains fixed.
Yeah. So let's just say that a little bit more slowly for your listeners. So if you have a circle with center O, and you have some point P, this looks maybe like 3 radii away or something, whatever the radius is. Let's say this is 3 radii away from the center. Then the inversion will be 1/3 of a radius. So if this inverted point, I don't know, p tilde or something, it'll be on the same radial line. So the equation is that OP relative to the radius should be inverted with respect to OP p tilde.
Exactly.
That's exactly what you said.
Yep.
If
Exactly.
you think of the circle as being a unit circle, then it's just x goes to 1 over x.
Exactly. Yep.
Okay.
And then it's a fact that I don't know when people learn this. I know I just kind of happened to learn it through like kind of math competition facts or various kind of, cute geometry you learn along the way as a young mathematician. But inversion will map certain circles to lines. And if you invert in the right way, then two of these circles will become lines, and then the other one will become a circle, and then it becomes trivial to find solve this tangent problem. You can just see the solution.
Beautiful. And let's just write those facts down for the people that are following along.
Yeah. So let me all write this. Okay. So facts.
Right. So if you invert a circle in a circle, you'll typically get a circle. In other words, if we do the same mirror, so here's our mirror O, but instead of taking a single point, if we take all of the points on a circle, so here's my circle C, then that will invert to, like, this point will invert to a point here, but the other points will also invert to other points, and we'll get a circle C tilde. And the point is that this circle, if this circle is C, then the inversion is C tilde. So that's fact one, maybe.
Yep.
And fact two is exactly what you said. When that circle happens to be, like, if I think of blowing up this circle, so if I take C and I start making it larger and larger, and larger and larger, and larger and larger, then it approaches a line. And the points on this line get infinitely far away from the origin, which means the points, if I start blowing up the images under the inversion of these circles, then I get something that's getting closer and closer to the origin. And so that's exactly what fact two is. The inversion of a circle, the inversion of a line is a circle through the origin. And conversely, of course, because the inversion is involution.
That's right.
So with those two facts, draw 3 random tangent circles.
Yep.
And by the way, we should say that inversion that we discussed can be done by straight edge and compass.
Okay. That I didn't know off the top of my head. Okay. But I guess that, okay. Well, okay. I guess it's an exercise, but okay, sure. Okay.
I can explain why, but it's we can come back to that in a second.
Okay, sure. Okay. And okay, so based on what you just said, Alex, then one thing you can do is you can say take some well, okay, there's not a unique circle, but let's just take some circle whose center is right
beautiful
here at the point where these two circles meet, right?
Yes, this to me is the magic of this proof. This is the kind of thing that I love, because you're like, where's the mirror? There is no mirror. You choose the mirror, but you choose it in a very particular way, which is exactly what you did, which is to put the center at one of the points of intersection. That's the key idea.
Right. Because we knew from the previous fact that if you invert a circle that passes through the circle that's doing the inverting, you get a line. That you know that to get 2 lines, then 2 of your circles had better go through the center of your inverting circle. Right?
Exactly.
Right. And so if we do the inversion with respect to the blue circle, then what we'll get, let me draw it in green, say. So then those 2 circles that go through the center of the blue circle will become 2 lines.
Yes.
And the other one will still remain some other circle, but it has to touch the other 2. So it's going to look something like that. And then now you ask, well, can I find a third thing that's tangent to all of these? And then it's pretty clear. It's pretty easy to draw that circle, right?
Exactly.
You just draw it, no problem. So I don't know. It's this guy, right?
You take an arbitrary configuration by this mirror to a trivial configuration, solve it trivially, and once you've solved it, of course, you invert it right back.
That's right. This is basically, I think this might be most familiar in sort of maybe linear algebra terms. You've conjugated the problem, right? And in linear algebra, you learn that if you have a complicated matrix, you could always conjugate it typically to a simpler matrix or a simpler basis, right?
Exactly. Okay, great. So So once you've drawn, now there's something curious that happened here. You drew the circle below, this yellow circle,
Ah,
but you could
there's
have
another
also
one.
drawn one. There's another one.
Yeah, yeah.
And it's obvious that there's another one when you look on the right.
Oh, yeah, it's the one that rather the one that in the inside versus the one that circumscribes it, right? So
Exactly.
yeah, so there's this inside one, and then there's okay, I have enough color. So then there's this.
You can keep it yellow. It doesn't,
Yeah, okay. Okay,
because
sure.
they're the two solutions.
Yeah, sure. Okay. Yeah.
All right, so now we've proved Apollonius' theorem. Apollonius' theorem is that given three tangent circles,
Mm-hmm.
there are exactly two circles tangent to the three given ones.
Mm-hmm.
And the construction, straightedge compass construction, now, if you actually try to do this operation with straightedge compass, it's like 100 steps. It's very, very tedious. And in fact, a colleague of mine, Arthur Barragar, and I wrote a paper which gives what we believe is the shortest construction.
Without doing inversion.
Without doing inversion. The proof that the construction works, the proof we give goes through inversion. But the construction itself is purely straightedge compass.
Wait, I thought you said that inversion itself was a straightedge and compass operation.
It is a straightedge compass operation, but it costs a lot of. So there's this great book. I don't know if you're familiar with Hartshorne's algebraic geometry book. Mm-hmm. This is something that sort of all algebraic geometers
sure.
read. Hartshorne has a Euclidean geometry book for kids, meaning college students or something, where he has this great notion of it's kind of like a golf metaphor. So there's the par that a certain construction is a par 4, but it can be done in 3 or something. So I'll give you an example of that. If I give you, there's another sort of classic geometry thing. If I give you a line and a point not on that line, can you draw the perpendicular line? How many steps does it take to draw a perpendicular?
I forget what the base steps are, like 1, say, or 2, right? I don't know. You just
so here's a line and here's a point not on that line. So there's like the standard thing. I remember I was taught, you take your compass and you put it at this point, and then you draw this circle.
Mm-hmm.
And then you take a compass, put it here, and draw a circle here. And then you take the compass, put it there, and draw a circle there.
Ah, okay.
And now you have your perpendicular.
Okay. Clearly, I haven't thought about this for a while because I thought it's one step because I just, whatever, like just, I don't know, compute some dot product or something. I just, just dropped it, right? But okay, I forgot how limited you are with a compass. But okay. Yep. So it's like,
if you have
how
2
many
points,
steps?
You can. Yeah. So how many steps was that exactly? How many steps?
Looked like what? 1, 2, 3, 4. Is that right?
3, 4. That was 4 steps.
Okay.
4 steps.
Okay.
But in fact, so this is a par 4, but can be done in 3.
Oh.
So how do you do it in 3? Here's another line and a point.
Okay.
Do you want to think about it for a second? I don't want to put you on the spot, but
okay. But is it okay? I'm trying to think. Does it involve a modification of this, or I have to really
it's a very slight modification of this.
Okay. Let me just see if
Let me just tell you.
Okay, sure. Okay, go ahead. Yeah.
I don't want to put you on the spot.
That's
it's this first step that was completely unnecessary. Just take any point here and draw this circle, and take any other point here and draw a different circle. They'll still give you a perpendicular here.
Oh.
There was no reason to draw a first circle and have them be equally distant.
Ah. Oh, okay. Oh, interesting.
So just forget about that first step and put a point anywhere and put a point anywhere here and draw this circle and draw this, completely different circle. They'll still intersect at a point that's orthogonal. Okay. That'll still give you that second point. So that's how you do it in 3 steps.
Okay. Wow.
But here's a crazy one. So this one really, what if I have a line and a point on the line? How do you do that?
Oh.
So in 4 steps, it's still the same argument. You can draw this circle, then you have your point here, and you can draw that circle and that circle. And now you have the 2 points that you can drop the perpendicular through. But is there a way to do it in 3?
Yeah,
I'm
I'm
you?
not going to be. I'm not going to be able to figure this out.
Here's the crazy thing. So when I saw this, that's when I said, okay, I have to read this book. I now appreciate what this book is doing. Here's what you do. You take a totally arbitrary point somewhere off to the side. Okay, what is that doing there? You put your compass there and make a circle with this radius, with the point that you want. That'll hit the line at one other place.
Mm-hmm.
That's one move, right? That's one use of the straight edge or compass.
Oh, I
Now
see.
I have
Okay.
2
Oh, I
points.
see. Picking an arbitrary point is it doesn't cost.
Yeah, it doesn't cost because
Okay.
you don't do that with the compass or a straight edge.
Got it. Okay.
You just
Got
put
it.
a point
Okay.
there. Right?
Yeah. Okay. Okay.
Then you have these 2 points, so you draw a straight line.
Okay.
And now this point is going to be perpendicular.
Hmm. Hmm.
Because this angle is 180 degrees. So this angle is going to be half of that.
Let me see if yeah, that's right.
Isn't that crazy?
That is, yeah, that's pretty amazing. Yeah.
So you can still do it in 3 steps, but it's but the argument is a much more. Okay, so this is like, high school 9th grade geometry, right? Nothing here is yet headed towards. It looks like we're just playing around.
Yep.
And that's what I like about this problem. You just keep playing with it, and you keep it just keeps getting deeper and deeper and deeper and deeper. So again, if you could draw 3 tangent circles, please. Great. So then we had those 2 yellow solutions, one on the inside and one on the outside. And so apparently it was Leibniz that first realized that what you're really doing when you draw those yellow circles is there's this curvilinear triangle, this region between the 3 points of tangency, and you're inscribing a circle in that. And once you've done it once, there's nothing stopping you from doing it again and again and again.
Yep. That's right.
So if you draw a couple more of those.
Yeah. So it's going to be hard to draw, but I guess I'll just highlight the regions that you just talked about, right? Because you have this sort of curvilinear triangle there, and if you sort of blow it up, let me redraw it to the side because it's getting quite small. So like if you sort of zoom in, then you'll have this region that looks like that. And then you could repeat the process. Let me use a different color. Yeah, right.
Yeah, but you don't have to just do it inside that green. You can do it in all the other ones too. You've made 4.
Oh yeah, that's right. Yeah, that's right. Yeah. So there's sort of this region, that region, and then that region as well.
Exactly. So you can put circles in each of those, right? You can put a circle in here. You can put a circle in here, and so on. So everywhere you have a little gap, you just put in a circle. All the way around. Okay.
Yep. Yeah.
So now, so that's called this thing. When you start with 3 tangent circles and you continue this forever, it has become known as an Apollonian circle packing. Even though Apollonius never drew this object, the earliest thing that we know of it is in notebooks of Leibniz. But so maybe it should be called a Leibniz packing. Who knows? But
I see. So Apollonius was the one who asked about the compass construction for a single version.
For a single, yes.
Right. And then Leibniz was the one who iterated this. Forget the compass part, but just iterating these.
Or use the compass, but just use it, a million times. And
sure.
In fact, use it infinitely many times.
Interesting. I didn't know that seems. I don't know. Leibniz. I think of calculus. I think of philosophy, like circle packings, where like he was a
geometry. Calculus is a branch of geometry. Right? You just want to compute areas. We know how to compute areas of rectangles and circles and stuff like that, but can we compute areas of arbitrary things?
I see. I mean, okay, so if you're going to iterate this, then there's a limiting process and
limits.
Limit.
Absolutely.
Okay, great.
And infinity and all that good stuff.
Okay.
So let's call this thing a packing. So this is called an Apollonian packing. Let's call it P, curly P, something like that. Now, we didn't draw all the circles. We only drew some number of the circles, right? But we sort of imagine this infinite object. It's clear. I think people can imagine what
Sure.
this thing is.
Sorry. So is an Apollonian packing some finite, possibly or possibly infinite iteration of this, or does it have to be infinite?
The packing, but by the definition of the packing is that it's the infinite object at the end of once you've put in all the circles.
Got it. Got it. Okay. And is it also infinite? Trying to think. Is there anything going on in the exterior of the largest yellow circle, or is it everything just nested inside?
It's everything nested inside, because if you want to think about these circles as actually being disks, so these disks are all have their interiors pointed inside. Their normals are inside, whereas this one is pointed outside, so that the interiors are disjoint. So it has the opposite orientation.
Ah, got it. Got it. Okay.
So if you want to think of them as disks, this is a disk with the opposite orientation.
Okay. Got it. Okay. Okay.
And so so given one of these packings, of course, when we draw this thing, we're only going to draw finitely many circles. And so you might ask, given some parameter, like we're only going to draw circles with radius at least 1/1,000 or 1/1,000,000, right? We're not going to get circles too small. So given a parameter x going to infinity, can we say something about how many circles there are in the packing with radius at least 1/x? Like if we're only going to draw finitely many of these things, and maybe we want to get finer and finer information. So what can we say about this? And so do you want to take a guess at what the growth rate is?
Yeah, it's interesting. I was trying to think. First of all, I was like, this is just me being this. I was like, oh, why didn't you use epsilon somewhere? It's like x is like a funny variable. I don't know why I was kind of caught up on that, but okay.
You can use epsilon. Yeah.
I don't know why.
If you like epsilon goes to 0, how many of them have radius at least epsilon?
Yeah. Okay. This is just sort of like, I mean, you're a number theorist. If you used x as an integer, you'd also be like, what the heck? Why didn't you use n or p or something, right? And I don't know why. I was having a moment where like, why is this not epsilon and this is x? Okay. Yeah. Anyways, okay. I'm just being silly. Okay. I'm sure like if somebody used a variable for like a prime that wasn't like p or something, you'd also be kind of like, right? Okay. Anyway, I'm being silly. Okay, we get it. Because here's what's going through my mind, right? So it's like, okay, so I feel like this is a two-dimensional problem. So like there's probably like that's probably significant in some sense. Because you could, I guess you could ask this question in higher dimensions, right? So like, okay, so there's like, I feel like there's the two-dimensionality, or I think. So that's probably like the first like largest bit of information, how I would guess the growth rate. And then the second order consideration is how much does this growth rate depend on the initial radii of your circle, like your seed configuration, right? And I feel like that's maybe like a next order correction, if you will, to like the fact that you're in two dimensions, right? So that's like sort of like what's going through my mind. Now to turn those into actual numbers, I'd have to think about it a lot more. Yeah, I feel like I'm not smart enough right now to give an actual number, but those are the ingredients that I see.
That's exactly right. Those are exactly the ingredients. So there's a theorem that the number of points here will grow like some constant times x to some power. That power is something like 1.305 something.
Okay, I would have never guessed that.
This number is the Hausdorff dimension of the fractal. So we can talk about Hausdorff dimension in a second.
I was going to ask about that, but I didn't want to like go to a complexity depth too quickly. But because with the way this was, the way we were drawing these nestings, it reminded me a lot of the Cantor set. How the Cantor set, you keep removing these thirds, and you don't remove the entire interval. You still have something left over that's a fractal. And I was also thinking exactly of just that, but I didn't want to like get too deep yet. Okay, but I'm glad this came back. Okay.
It's exactly what you said. The Cantor set is a one-dimensional version, or I mean, it's less than one dimension, but it's a version of the Sierpinski triangle. So the Cantor set is you take the middle thirds out, right? And you take the middle third out, and then you take the middle third out. The Sierpinski triangle, you take the middle triangle out, and then you take the middle triangles out, and then you take the middle triangles out of those. And so the Apollonian packing is exactly the same thing as Sierpinski, except you have curvilinear triangles. And instead of taking triangles out of the middles, you're taking circles out of the middles, discs out of the
Okay.
middles.
Okay. Yeah, I've never actually thought about the Serpentine triangle, but okay, makes sense. Yeah, I've seen like pictures of it. I just like never like actually thought about it. But okay,
Yeah.
sure. Yeah.
So this is great because these objects, the Cantor set, and the Sierpinski triangle, we can actually explicitly work out what their Hausdorff dimensions are. Should we talk about dimension for a second? So let me just so that there's not an untrue statement here. Let me put 1 plus little o of 1. In other words, it's asymptotic to this. And let me just say one more thing. The constant depends on the packing. The constant in front. I said this growth rate. This growth rate is some constant times x to the dimension. The dimension does not depend on the packing. It's a number. So all of these Apollonian packings, regardless of the starting configuration, have the same dimension. Let's see, I can be using this. All of these guys have the same dimension.
I see.
But not the same constant in front. So the growth rate, as you said, is something that's geometric, whereas the sort of the next order thing, which is what's the constant of the growth rate, depends on the particular.
All right, package. I was spot on. I just want to think this is a meta comment because it just happened live, but somehow like as mathematicians, like once you get to a certain level of depth, like you have like a sort of like intuition for things, even though you've never seen the problem, and that exactly just happened right here. Right? Like I've never seen this problem. I just kind of like sniffed what it had to be, but it's just to illustrate a point of like how mathematics can really give you a lot of power to think about things.
And that's exactly right. It's what it has to be, and in fact it is. So that this is the theorem. So in this version, it's a theorem due to myself and Heo from
nice
from a couple of years ago.
Oh, that's funny. Actually, Heo was a postdoc when I was an undergrad at Caltech.
Oh, cool.
Yeah. Anyways, math is a small world. Yep.
Yep. So let's discuss these dimensions. Okay. So we're not going to do Hausdorff dimension because that'll take us too far. But sort of naively, naive notions of dimensions, which will be good enough for our purposes, just so that your listeners who haven't seen fractal dimensions before can at least get their hands around it. So if I take an interval and I scale it by a factor by 2. So now instead of going from 0 to 1, it's from 0 to 2. This is how many copies is this of the original? In other words, here's the original. So I've scaled it up by a factor of 2, and now I have
2 copies.
2 copies. Okay. And if I take a unit square, so 0 to 1, and I scale it by a factor of 2, so let's just call that times 2. Right. So now I have a 2 by 2 square. And the question is how many copies?
4 or 2 squared.
4. And if I take a cube and I multiply it by a factor of 2, then of course I'll have 8 copies of the original. So the number of copies is 8. And 8 is 2 cubed. And that's exactly where the word comes from. And 4 is 2 squared, and that's exactly where that word comes from. And this is the 1. So the dimension is sitting here in the exponent. Our naive notion of dimension can be, if you take scale by some factor, let's say alpha, then the number of copies of the original, if the thing has some self-similarity, some structure, then the number of copies will be alpha to the dimension. Does that make sense? How this pattern matches the patterns that we saw for the usual objects? And so the dimension is like log of the scale of the number of copies. We'll see that in a second. So if we go back to the Cantor set, so if I take out this middle third, and then I take out that middle third, and I take out that middle third, and so on. If I scale this by a factor of 3, so instead of going from 0 to 1, I go from 0 to 3. The first thing I'll do is I'll take out the middle third, which is from 1 to 2. And now I have another Cantor set that I'm about to draw here, and another Cantor set that I'm about to draw here. So the number of copies of the original is 2. And 2 should be 3, the scale factor, right? 3 to the dimension. So 2 is 3 to the dimension. So the dimension of the Cantor set dimension of the Cantor set, if I unwind this, is what log base 3 of 2, which is some number. I don't know, 0 point, I'm going to guess 6. Does that make sense?
So when you go from 0 to 1, then you times 3 to go from 0 to 3. The Cantor set is defined by removing the middle third, right?
The middle third.
And so
I'm going to not scale it by a factor of 2. I'll scale it by a factor of 3.
Mm-hmm.
And when I scale it by a factor of 3, how many copies of the original do I get?
Yeah, that's what I was trying to think. How did you get 2?
Because what do you do when you take an interval is you cut out the middle third.
Mm-hmm.
And then you cut out the middle third of that.
Oh, I see.
The middle third of that.
Uh-huh. Wait, so, okay, because when you cut out the middle third of 0 to 3, you get back 2 copies of the original.
You get 2 copies.
Yeah, okay, that's okay.
You can compute. So you want to draw a Sierpinski triangle for us?
Sure.
So just draw some random triangle. Yep.
Mm-hmm. Yeah. Actually, just to so when you said naive dimension, I think what you're describing is this is an intuitive way to think about the Hausdorff dimension without getting into all the nitty gritty details about Lebesgue measure, right? Which would
and
for
Hausdorff
a nice
measure
right,
and
for a nice set, this is going to work. For your general measurable set, you have to be more careful. Right?
Much more careful.
Yeah. Okay. Great. Okay.
So let's do it just with nice sets where we can compute the answer explicitly.
Exactly. Yeah, that's right. Okay. Yeah.
So if you draw a Sierpinski, so just draw a triangle.
Mm-hmm.
Doesn't have to be equilateral. It can be funny shaped.
Sure. Okay.
But okay, for our purposes, let's make it equilateral.
Sure.
So get the midpoints of the 3 sides and connect those up to make a triangle.
Mm-hmm.
And that's what we cut out.
Mm-hmm.
And then do it again for the 3 subtriangles.
Right.
So I don't know how you want to draw cutting out, like shade them in or something.
Yeah. I'm trying to think okay, I guess.
Or just leave it. Just leave it like that. I think it's fine.
Okay, sure.
Like that's what got cut out. We'll just sort of keep track of.
Yeah. Maybe I'll use it. I'll just use it in red. Just like whatever got these get cut out, maybe.
Yeah.
Yeah, there you go.
And then again, we would do that for all of there's sort of the triangles that are standing up, that are sitting on their base, or the triangles that are any triangle that has a base up above the triangle is the removed triangles. So the triangles pointing down, we've removed. The triangles pointing up, we keep.
Right. Yeah. Okay. Yep. That's a good way to think about that. Yeah. Yeah.
Okay. Mm-hmm. So let's say that it was equilateral, and let's say that this was 0 and 1. So let's say this was 0. Oops. Let's say this was 0 and this was 1. Mm-hmm. How would we work out the Hausdorff dimension of this thing?
Yeah. So I guess by the same trick, suppose I, I think there's something similar with that 1/3. Like if you
let me suggest that we double it.
Yeah. Okay. I was trying to figure out the right thing. Okay. So 3x wasn't the right scale. 2x would be the easier one. Okay. So if we doubled it,
because we take midpoints. As the start of the construction is to take midpoints.
Yeah. I was confused because when you take midpoints, then somehow there's like kind of like this 3 triangle thing going on. That's why I was a little confused. But yeah. Okay. So if you let me just do some thinking on the fly here. So if you did this doubling thing, right, then what you would do is you'd have something like this. Right. And
yeah, I think of it as going from 1 to 2. So 2 is over here. And then you have like a triangle that big.
Sorry, I didn't draw it correctly. Okay, yeah.
But it's okay. I mean, it's the same idea.
Yeah, okay. Oops. Oh, I see. Yeah, okay. Let me just yeah, okay, got it.
I'm just stretching from 0, 1 to 0, 2. So I'm taking the whole thing.
Actually, I think I drew the same. I think it's just you embedded this guy into the lower left quadrant. I embedded it to like the top of the pyramid, so to speak.
Yep.
It's the same concept.
Same exactly.
Yeah. And in this case, then I think I see what's going on. So here, if you do that, then you have 4 copies of your original triangle, right?
Well, we're going to take out the middle.
Right. And when you take out the middle, and
so how many copies do we get?
Yeah. So
we get this one down here.
Right. Sorry, you only take out the middle one first. When you take out the middle one first, you get 3 copies.
Yes.
Yeah,
that's
right.
So when we scale by a factor of 2, we get 3 copies of the original.
Instead of 4. I see. So now you have right. So if it were 2-dimensional, you get 2 squared. Now you get 2 to the log 3 of 2. Sorry, logged to the base 2 of 3.
Right.
Right?
I'll just write that down again. The number of copies is equal to the scale raised to the dimension.
Yeah. So right. So this is it's exactly what I just said.
It's exactly what you just said. So the number of copies is 3. The scale, we scaled it by a factor of 2 to the delta. So now delta is log base 2 of 3.
Yep.
Which is like 1 point, what is it? Whatever it is. It's 1 point something. 1.3, 1.4.
Yep.
I'm just going to put a number here at random. But it's some number.
Yeah.
Right.
Yeah.
So that's the Hausdorff dimension of the Sierpinski triangle.
Yep.
And notice that it's bigger than 1. It's bigger than 1 because this entire line, like these lines, which have dimension 1, are fit inside, are still in the triangle. And it's less than 2. It's strictly less than 2 because when you take out all of those triangles, all of them, now there's actually no area left. The area is all gone, and all that's left is some fractal dust.
Right.
So that's what that's sort of the notion of fractional dimension became fractal.
Yeah, I can't help it. We could just say it maybe 2 words. Like, to make this rigorous, I mean, I've looked at the definition before, but it's been a long time. It's something like, I think you have to like basically the dimension is some kind of like lim inf or lim sup, however you define it, of like, how to say, a dimension is basically a probe, right? And if your dimension is too high, you won't capture anything, or too low, one or the other, right? And this critical dimension exactly captures the behavior. And the way the Hausdorff dimension is defined is like you kind of like cover things, you put an exponent, and you choose the first exponent such that it's like non-trivial, or the only exponent where it's non-trivial.
Exactly. Right? There's a, when you cover and you take this limit, either there's a series with this exponent delta, and that series will either diverge or be 0 for all values of delta except for 1.
Right.
And so that magical value of delta, where it's not 0 and it's not infinity, well, where it's the cusp where it changes. That's the Hausdorff dimension.
You're going to like cover your set with a bunch of, I don't know what to call it, like sets. I don't know.
Yeah.
Let's
say U alpha
or U alpha. Yeah. You're going to cover with U alpha, right? And let's say that
with
these
radius epsilon, with radius at most epsilon.
Okay. And the or the diameter or radius.
Diameter,
say. Yeah, you're gonna let epsilon go to 0, and then you have to take the Lebesgue measure of that raised to some power or something like this, right?
Right. So what you'll do is you'll sum. So if you have a cover, if your set S is contained in this union of over the alpha, then what you do is you take the areas of the alphas, of the area volume whatever of the U alpha raised to the exponent delta, sum over alpha, and then limit as epsilon goes to 0. And then for almost all values of delta, this limit will be 0 or infinity.
Right.
Exactly. And where it transitions from being 0 to infinity is your Hausdorff dimension.
Exactly.
So that's more or less the idea, although it can be even more sophisticated than that. But
sure. Yeah. Okay. Great.
If you introduce Hausdorff measures and anyway, that's basically the idea.
Okay. So this is basically the definition of Hausdorff dimension, right?
Yes.
Okay. Cool. All right. Awesome. All right. Great.
So now we know so how do you prove? I mean, I could tell you a little bit about how to prove. There was this theorem. I forget what slide it was. 2 slides ago. I'm back on number 4. I could tell you a little bit about how to prove this theorem, but maybe that'll take us a little. So this is where it goes from something easy to now we need some rather advanced topics. Maybe we'll come back to that theorem if we really want. Sure. So that's the Archimedean theory. This is all geometry. We haven't done any number theory. I'm a number theorist.
Okay. Okay.
And let's put back that 3 1 2 3 2 3, which was a 3 4 5 triangle picture. And then we have this guy in the middle. Okay, so this has radius 1. This has radius, well, you drew it here. You drew 3's and ones and twos. And so the question is, what is this radius?
Yeah, that's right. Right. And
That inner radius.
right. And we agreed that there's no good reason I should know what that is.
There's no good reason that you should know what that is.
Yeah.
But there's a gorgeous theorem of Descartes.
Well, how appropriate. This is the Cartesian Cafe after all.
This is the Cartesian Cafe, so we got to get Descartes in there. So he was having this correspondence with Princess Elizabeth. This is in 1630s or something, and as part of this correspondence, he discovers, and this is sort of where the first hints of Cartesian coordinates also arises. I mean, people really cleaned this up a lot after his writings, but so he has this beautiful theorem that if you have four mutually tangent circles, so if I have four circles that are mutually tangent, let's see the way I've drawn them. I guess I'll put the last one over here. So the theorem is given four tangent circles, if so, it's convenient instead of radii. Let's call bend. So the bend of a circle, the bend is 1 over the radius, the reciprocal radius. Okay, so if their radii are, or their bends are B1, B2, B3, and B4 is the bend of the outermost, then there's a beautiful relationship between them, which is that the sum of the squares of the four bends is half the square of their sum.
Wow.
So that's a beautiful theorem.
Yeah, where did this come from?
That's what maybe I'll be able to explain.
Okay.
I mean, there's an elementary proof, of course, but there's a much deeper reason for this to exist. I mean, that's sort of the...
Okay,
yeah.
this is right. I feel like, okay, if something's due to Descartes, I feel like this is something we should have been taught all as kids or something. I don't know why did I not know about this fact? I feel robbed.
That's exactly how I feel.
Okay.
Because I also didn't know this fact as a kid, and there's no reason for me not to have known it as a kid. And I think I would have enjoyed it as a kid.
Actually, just while we're on all these tangents, so like, like the apocryphal story, I think of like Descartes with Cartesian coordinates was like he was sick. He was like looking at a fly in the room, and it's like, oh, how am I going to track this fly? Cartesian coordinates, right? I don't know. So that's like very far from the truth, apparently.
Yeah, like Newton's apple. There's lots of stories we like to tell ourselves. They're good stories. I mean, I don't mind the stories.
Okay, but Descartes didn't have a fully fleshed Cartesian coordinate system.
Well, it's kind of amazing. This will take us a little too far off tangent, but
okay.
The way that he tries to solve he returns to the Apollonian problem. So people return to the Apollonian problem again and again and again throughout the history of, for the 2,000 years after Apollonius, and they keep finding new stuff that Apollonius missed. Wow. Okay. And it's rather, I mean, this is why I like this problem. It's something that's, as you see, this is algebra. This is 8th grade algebra and 9th grade geometry. Like this, much of this story can be told in that framework. Okay, so given this fact, let's see if we can work out what this last radius is.
Right, because it's just a quadratic equation.
It's just a quadratic equation.
Okay. Yeah.
Okay, so the bend, if the circle has radius 3, its bend is 1/3.
Oh, sorry. I guess. Yeah. Okay. I guess. Sorry. You have. Oh, right. Okay. You have 3 out of the 4, right? You don't have because you could have had previously we had the outer one too, which would have been 5. But okay, we have 3 out of the 4. Okay.
We have 3 out of the 4. Exactly.
Yeah.
Exactly.
Okay.
So this circle has radius 1/3, has bend 1/3, radius 3. This one has bend 1/2, and this one has bend 1 and radius 1. And actually, it'll be easier if we scale everything so that the bends are all integers, just to make our lives easier so we don't have to deal with fractions.
Sure. So
if I take this whole thick picture and I shrink it by a factor of 6, then this radius becomes 1/2, so its bend is 2. This radius, which used to be 3, so I'm going to scale everything by a factor of a 6th. So the radius is now 1/2. So the bend is 2. The bend is the reciprocal radius.
Mm-hmm.
Right? If the radius used to be 3 and I divide it by 6, I get a radius of 1/2.
Mm-hmm. Mm-hmm.
What used to be a radius 1/2 is now, what used to be radius 2 when I divide by a 1/6 now has radius.
I was just going to think about it in terms of bends and forget
Okay.
about the radii. Yeah. So
Yeah,
just
beautiful.
basically multiply the bends by a factor of 6.
Beautiful.
Right?
Yeah.
Yeah. Okay.
So 6 times 1/2 gives us 3, and 1 times 6 gives us 6.
Okay. Yeah. You're labeling by bends now instead of
I'm
radii.
labeling by
Perfect.
bends
Yeah.
instead of radii.
Great. Okay. Mm-hmm. Yep.
Okay, so now we have everything we need except for whatever the last bend is.
Yep.
So should we do it? You want to do it?
Sure. Okay. All right. Live arithmetic, which is not
Live
my
arithmetic.
strength, but okay, let's do it.
This arithmetic is not so bad.
Okay. Yeah. Yeah. I'm sure I can do this. So we have
Okay. So the sum of the squares.
Right, 2 squared plus 3 squared plus 6 squared plus the bend squared that we are missing equals 1/2. 2 plus 3 plus 6 plus b squared.
Beautiful.
Right? Okay. So let's work this out. So then we simplify so that's going to be 4
plus
9 36, and this guy is going to be 11, right? So then now we have b squared minus 22 b, and then minus 23.
Minus 23. I
think it looks like you could factor this, fortunately, right?
Yeah.
So this is because this is b minus 23, and then b plus 1
Beautiful.
equals 0. So then b has to be 23. It's the positive solution to this, right?
So b is 23.
Wow.
So that inner guy is 23, has bend 23. So its radius is 1/23.
Right.
So if I scale it back by a factor of 6, instead of 1/6, this radius is going to be 6/23.
Yeah, I would have never, ever guessed that. Yeah.
Pretty cool.
Yeah. Mm-hmm.
Okay. 2 observations. 1, we discarded this b is -1 solution.
Mm-hmm.
But what is it?
I'm tempted to say it's like maybe the larger circle, but that doesn't seem quite right.
It is exactly right.
Okay.
That's exactly right. So Apollonius says there's 2 solutions. There's one solution on the inside. There's one solution on the outside.
Okay. But how did so this minus, but how do you interpret that -1, right?
That minus is that its interior has the opposite orientation. All of these have their interiors on the inside.
Okay.
And this outermost circle is oriented the other way.
Okay.
It's externally oriented. So that's why its bend is -1 and its radius is 1. I mean, -1 is its sine radius.
So its magnitude is still the correct.
The magnitude is the correct thing, and the orientation is the correct orientation.
Yeah, that's amazing. That's amazing.
To be pointing out the other way.
Okay. That sign confused me, but okay. Now that you've drawn the interior, now it makes sense. Yeah. Okay. Yeah.
So this is the beautiful thing, because this is exactly what happened to people like Descartes. You know, they saw this, they said, "Oh, this is kind of cute," and then they're like, "Well, that -1 doesn't make sense." Actually, it makes complete sense when you put in. It's trying to tell you something. Like sometimes a mathematical solution that you just could calculate, and you get some nice answer, and you discard maybe some other answers. Like those answers have meaning. So this is a fun.
Yeah, I want to say that because actually let's actually even back up, because we didn't quite cover this even with inversion, and I was trying to recall how to think about it properly, because things make more sense when you add the point at infinity, of course, or they only make sense when you add a point at infinity, because you have to if you're going to move circles to lines, right? Because that point through the origin has to go to infinity, and once you start thinking about things at infinity, then you're on the sphere. And then I was trying to think again. I think these have to do with Mobius transformations, if I recall correctly.
That's exactly right.
Right. And what I want to say is, because all of this makes sense in terms of like thinking of this larger space of interior, exterior, point at infinity, then what I want to say is there's something deeper going on here, which is that this is a manifestation of geometry on this larger space.
Yes,
right? Right.
that's
Yeah.
exactly right. That's exactly right. And that's sort of where I eventually want to make my way over to.
Sure. Okay. Okay.
But
Okay. Yeah. Yeah. Yeah.
but first, there's one other thing that I want to point out,
hmm
which is that the radiuses, the radii were one half, one third, one sixth, and the new radius was 1/23. So the new
Uh,
bend,
mhm,
the new
mhm.
bend is 23.
Yep.
So
Yep.
this was a 2, a 3, a 6, and now we got another whole number, 23.
Yep.
Isn't that weird? We're doing like circle inversion and straight edge and compass, and the thing is still an integer.
Yeah. Yeah. That is quite amazing. Yeah.
So that's an observation that waited another 300 years from Descartes to a guy named Frederick Soddy. So what Soddy observed, so again, I'm just going to put the same circles back up. Let's say
Yeah.
it was a radius.
Yeah. Can you spell the name Soddy? I've never heard of
Soddy.
that name.
Soddy. So Soddy, Frederick Soddy,
Mm.
Frederick Soddy was a Nobel laureate in chemistry
Wow.
for having discovered isotopes and coined the term isotope.
Mm.
And he was messing around with mechanical construction in which he needed a bunch of tangent spheres together. And he computed a bunch of, he actually wanted to build this thing, and he did build this thing out of ball bearings, and he's got a picture of it in his paper on this topic. And he realized that the radii were all 1 over an integer, the way he had set things up. It's like, why the hell is that? What's going on?
So he was building some like models in his lab or something.
Yeah.
Yeah. Okay. Okay.
Yeah, he's
okay.
building some machine that had spherical parts, and then he realized the same thing is true for cylinders. So if you imagine like running a bunch of different size things inside a cylinder, and how would you pack them in an optimal way?
Yeah.
To fit in every little piece.
Ah, got it.
All these tubes running so the cross section of a cylinder is circle packing.
Yeah.
Of a cylindrical
I
construction.
see that. Yeah. 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 Yeah.
And so just to throw them back up, I think we had a bend of 2, then a bend of 3, then a bend of 6, and inside of here was a bend of 23.
Yep.
And the outermost was a bend of -1. There's this big outermost thing with a bend of -1. Right. And so he observes that there exist, so his observation is that there exist packings with all bends integers. Integral. And so why is this true?
Yeah, I guess packings in his case was like up to some finite iterations, right? I guess
Even though he was just a scientist and not a full-fledged mathematician, he understood that this process continues indefinitely. Maybe he didn't use the term infinity, but or maybe he actually did.
So you're saying he had the technical chops to realize that if you iterate this,
it continues forever.
Okay, because it's not obvious. Or actually, I see. Wait, because I see. I mean, okay, I guess is it an exercise that if you take Descartes' formula from before, that if and if you somehow start with a configuration that is integral or rational, right? Because you could always scale things, that you're always going to get a sequence of numbers such that when you recursively apply it, you will always get a rational number. Is that obvious? Or that's what you have to show essentially, right?
So it's not obvious, and it's slightly not true.
Okay.
If you start with a configuration of 3 equal circles, which have radius 1 and bend 1,
okay,
then the next thing that you want to put in, either here or here, starts getting like square root of 3s and stuff.
Okay.
So it's not enough to start with 3 things that have tangent that have integral bend. But if you have a 4th that has integral bend, then they will forever have integral bends.
Okay. So so is that like an exercise to prove?
And that's an immediate nearly immediate consequence of Descartes' theorem. Because if we think of exactly what we just did, if B1 through if B1, B2, and B3 are given, so we think of B1, B2, B3 as given, and B4 is the variable,
right?
then exactly as we saw, there are two solutions. So we get a quadratic equation B4. There are two solutions, B4 and let's say B4 prime, or B4 tilde, whatever we were calling that other guy, right? 23 was one solution, and B tilde was that other solution, -1, B4 tilde. So, in the quadratic equation, there's like negative B plus or minus square root. And so if you add the two solutions, if you add the two roots, the square root gets killed. And it turns out that this is 2B1 plus B2 plus B3. Let's see if that's right. In this case, B1, 2, and 3 are 2, 3, and 6. So 2 times 2 plus 3 plus 6. That's 11. That's 22.
Yep. Okay.
And on this side, I have 23 minus 1. So at least it's believable in our example. And in fact, it's a very elementary exercise in algebra. Now, why does this mean? I claim that this implies this fact, this Soddy observation. Let's call it a theorem. This Soddy theorem on the existence of integral circle packings. This implies Soddy.
Sorry, Soddy's theorem is that if you start off with a configuration of 4 integral things or rational things, then it repeats, right?
That's right.
Yeah. So
so let me try to convince you of it.
Yeah, because what I want to say, but I realized it wasn't quite. How I say, the thing that's confusing me is your integrality relation is such that you have to sum B4 and B4 tilde to get an integer, coefficient polynomial of the right hand side. So I'm just a little hesitant. Okay, so if I recurse this, well, I'm only going to get to put in B4 or B tilde 4. So I'm a little nervous iterating this.
Okay, so if you think about what's going on, when I start with 4 tangent circles, let me do it like this. So here are 4 tangent circles. There's a bit of circle geometry, which we've been talking a lot about already. But if you take these 3 points of tangency, so if I ignore the outermost circle and I take those 3 points of tangency, there's a circle through those 3. And let's see what happens if I think of that circle as a mirror.
Okay.
So inversion in this mirror, what happens to inversion through this mirror? So this mirror here, and I want to invert through it. So if you have a circle, so this is a circle, it does not go through the center of the mirror. So its inversion will also be a circle. These 2 points will be fixed. In fact, it crosses here at a right angle. So angles are preserved. So in fact, it turns out that what will happen is this segment will turn into that segment and conversely. So this mirror keeps this circle fixed.
Does
that make sense?
Let me think about that. Okay, so because the circle is determined by 3 points. 2 of those
3
are
points.
fixed. How do you know that it's fixed and not another circle that goes through those 2 points?
So if I have a circle that goes through another circle orthogonally.
Okay.
Then those 2 points are fixed, but the normal direction is also, or the tangent direction, it's also preserved under inversion, because that direction turns into that direction.
Okay, so it was the orthogonality that was
it's
key.
the orthogonality that's the third component.
Got it. Okay, so that's the third like constraint. Yeah.
Exactly.
Yeah. Okay. I believe it now.
Okay.
Yep.
So this bit turns into that bit, and conversely.
Okay.
This circle is also fixed under inversion for the same reason.
So, all three, except for the outer one. It's going to go.
Except for the outer one.
Right.
What's happening to the outer one? It becomes the inner one. So there's a map from the outer to the inner, which is keeping the other 3 the same, which is this transformation. Okay, but then there's another mirror, which is to take these 3 points of symmetry, and I can draw a circle through these 3 points. You kind of see that? And what will happen to inversion through those three?
By the same logic, the circles passing through will remain fixed because they're also all orthogonal, right?
Exactly.
And then the one that, let me get my point here. So this one is the one guy that's not.
Well, that's a mirror. That's not.
Oh, sorry.
This one's
this one's the mirror now, right? Or which one are we talking about? So this was the original mirror. And now you're talking about this guy being the mirror?
No, this was the mirror we were talking about before. And it was the mirror that took the outermost circle to the innermost while fixing the other three. Now I want to know what happens under this mirror to the original four circles.
Right. Yeah. So
it fixes three of them.
That's right. So this, right. So if this is the mirror, then right. So the three that it fixes will be, right, that one, and then the largest one.
Exactly.
And the one that's, yeah. So then there's this guy that's going to be non-trivial because it doesn't even touch the mirror.
Yes. Right? And where will he get sent?
By the same logic, it has to be, I mean, I guess it has to be this one, right? I'm looking at it right.
Exactly.
Yeah. Let me
exactly right.
Yeah. So let me draw it an even different color so we can. I think you should go to that one. Yeah.
Okay. How does this continue? There are two more mirrors in a similar. You see, how did we get this mirror? We ignored its outermost mirror.
Okay, I see where this is going now because basically, how do I say? Before we knew we could iterate the packing. It's just that we didn't have an algorithm to generate the successive packings from previous ones. And now this is what we're doing.
Yes.
Right? Yeah. Forgetting the picture for a second. What's going on? You have four circles. You take three. You get a mirror constructed from those three. That sends the leave one out circle, the fourth one, to the one that you want. And you just keep repeating, like leaving out the correct one and forming the mirror out of the three that are relevant. And you just keep iterating. Right.
Yep.
Yeah.
So before we leave this, our second green mirror, what happens to the red guy in the center?
So that must go to, yeah, in this case, it's kind of, I'll draw it in red as well to make it corresponding, but I think that red should could go to this guy probably, right?
Exactly. Because he was tangent to this circle, which is fixed. He was tangent to that circle, which is fixed, and he's tangent to that circle, which moves to that circle.
That's right.
So he has nowhere else to go but into that little area.
Yep.
Okay. There's another mirror, which is these 3 points of tangency. And there's another mirror, which is those 3 points of tangency.
That's right. And then you'll get all the other yeah, I'm thinking about for me, like the picture is getting a little crazy, but I think the combinatorics, it's easier to talk about the combinatorics. Because basically you always have 4 circles and sort of choose 3. And so there's 4 choices for that, right? And so each of those four choices of the 3 among the 4 will give you a separate mirror, and a separate mirror will give you a separate iteration of this packing, right?
Exactly.
And I'm guessing you just keep on doing that, where you now have your 4 becomes like throw away 1 and look at the new one, and then repeat that, right? And you just keep going.
Well, once you have these 4 mirrors, my claim is that if you just continue inverting in just these 4 green mirrors, you will get the entire packing.
Oh, you don't even need to change the. Oh, I see. Okay, I thought you might even have to change the mirrors, but you don't.
You don't. You just start. Okay. You just take these 4 green mirrors.
Okay.
And you just iteratively reflect through all of them. Reflect your 4 initial circles.
Okay. I see that now. Yeah.
So if we call these mirrors S1, or inversion through these mirrors S1 through S4.
Right.
My claim is that if you take the group generated by S1 through S4, and you act on your initial configuration, what should we call these? A cluster. C is the cluster of the initial 4 circles. Initial cluster. Then this is the entire packing.
Wow, that's awesome. That's really cool because from a purely group theoretical point of view, right? Like if you were to write this group in terms of generators and relations, well, okay, it's
Yes,
generated by the S1 to S4. Each of the SIs have order 2, but
exactly.
their multiplication table is extremely non-trivial just based on this fact, right? Because it generates this infinite set. Yeah.
It generates this infinite set, and in fact, the fact that the circles are disjoint, the interiors of the circles are disjoint, means that they're free. So this is actually a Coxeter group.
Okay, I actually don't know what a Coxeter group is.
All it means is that the squares, all the elements are involutions, all the generators are involutions, and and the products have to have some relation. And in this case, the relation is that S1 times S2 to the infinity is the identity. In other words, there is no power of S1 times S2, which is the identity.
Oh wow. Okay, okay.
So it's just free.
Yeah, let's just yeah. I'm just curious because I actually wanted to know what a Coxeter group is. So Coxeter group, right?
Well,
Or maybe you want, yeah.
Coxeter's work actually, I mean, depending on how much time we have, will become intimately relevant to this. But I don't know if we'll get there.
Okay, let me just wrap this up. Maybe this isn't quite right, but I think what you said, if it's a Coxeter group, say you have S1 through Sn and say n equals 4 in this particular case, then the fact that they're all reflections is just the statement that Si squared equals 1, and you're basically something like it's free, sort of like the sorry, not but like you're saying that the group generated by all distinct pairs like this is supposed to be a free group.
No, so usually by Coxeter group you have generators who that are involutions, their squares are 1, and the other relation is that S1 S2 to some power is 1. So
S1.
SI SJ to some power is 1.
Okay.
And that's the information that you put down. But that power might be infinity in the sense that S1 and S2, there is no power of S1 S2
Okay.
which is 1. And those are the only relations.
Got it. Okay, so
yeah, so there's a sequence of Nij, which are integers, possibly infinity, meaning there is no power, but that Si Sj to that power is 1.
Oh, so okay, so it's some I and J's, not necessarily all I and J's.
Yeah, there could be different ends for different pairs Ij.
Oh, sorry. Okay, so each Ij has an Nij.
Exactly.
I see. And that's it.
And that's it.
Oh, okay. I see. And
you can see how these things arise in circle packings and mirrors in general. That's what Coxeter, I mean, the way Coxeter got onto these things is he was trying to understand Euclidean mirrors.
Yeah, I was going to say, because I guess the simplest example of Coxeter groups would be just to take reflections through lines.
Yep, and planes.
In the plane, right? Although reflection through a line is a very special case of an inversion, and then more interesting Coxeter groups will come from inversions through circles, like we just had here.
Exactly.
Right? Okay. If you just took an arbitrary, so is this a Coxeter group? I just give you an arbitrary collection of circles and look at the group generated by their inversions, or is there some restriction?
The restriction is that the circles must intersect. If they intersect at all, they should intersect at angles that are pi over an integer.
Okay.
So that when you reflect in one and then the other, that number of times, you get back to the identity.
So if you don't have this integrality condition, how does that, where is the definition of Coxeter group going to go wrong?
So it's that when you reflect in one and then the other, you get a non-discrete group. The group will keep rotating. It's like an irrational rotation of a circle.
Yeah, but an irrational. Oh, I guess right. Okay, here's my real question. When you say something to the infinity equals 1, what does that mean? I guess if Nij is infinity, what does that mean?
Oh, you're saying why isn't that a Coxeter group the way I've defined Coxeter groups?
Yeah. It looks like Nij equals infinity is not a vacuous condition. It actually means something, and that's going to correct for this irrational rotation, right?
Yeah. Well, I think when people say Coxeter group, they do just mean this general in this generality. So that would include the possibility of any circles, inversions in any circles. But when you do Coxeter's, when you are trying to do Coxeter's classification of reflective lattices, you want discrete groups of symmetries, discrete groups of isometries. So for that to act, to be realized as an action of some discrete group on a lattice, then you do want this rationality.
I see. So then that's why in this more general setting, if those are all infinity, then you could have whatever irrational rotations you want because there is no condition. But you're saying for other settings you want all the Nijs to be finite.
Right.
Got it. Okay. Got it. Okay.
So the connection from the group theory to the geometry is a little subtle, but the abstract group theory, there's the abstract group.
Got it. Okay, great. Okay, all right. Yeah, all right. We went on a little bit of a tangent, but okay. All right. So yeah, why don't you resume?
So you agree that these 4 inversions will generate the whole packing?
Yes.
Right. That makes sense. Like you just keep moving your 4 circles around by these inversions, and you'll reach any circle that you would have drawn at any point in the. And you can sort of see that by. Like, how do you get this next circle? Let's see. Let me try to be consistent with the colors of the packing. How would I get this circle? I get this circle by moving this one across by moving this one across that big green guy. Right? And then how would I get that one? I get that one by moving somebody over here across this green guy, and that one I would get from moving this guy across that guy, and it sort of just keeps going.
Yeah, I feel like there's basically some kind of like there's like a code string you could write to like where things are in their nesting, and you kind of just can read off like what sends what where, because
exactly
right there's 4. You start off with 4 things, and then every time you embed something else, it carves it up into other regions, and you could just kind of you're just keeping track of the tree of like this, and you just kind of can read off how to write this.
Yep.
Yeah.
So, well, just to maybe take this in a slightly sideways direction. So Poincaré was a big proponent of when you're doing things, especially when you're doing like Mobius transformation, circle inversions in the plane, it's not really, the plane is the wrong object. The right object is to pull yourself into hyperbolic 3 space. So above, maybe this is going a little too far, but above the plane, so here's the plane in which our Jamboard is located. Okay, and in this Jamboard we have our 4 circles that we started with, and our whole packing, and then we have our dual. These are called the dual circles, the ones that inversions through which are going to generate our packing. So Poincaré says what's really going on is that these are not circles; they're hemispheres. They're geodesic hemispheres. So these are half spheres. And what we should really be doing is we should be thinking about inversion in the upper half space. So this is hyperbolic 3 space. This is a model, the upper half space model for hyperbolic 3 space, which for now just think of H3 is X, Y, Z with Z positive. We can just think of it as being that for now.
Yep.
Okay. And so if you take a point out here, you can invert it through this sphere in exactly the same way. And it turns out that if you take any random point and you invert it through the sphere, and you invert it through another sphere, and you invert it through another sphere, and you invert it through another sphere, and so on, eventually, every time you invert it through a sphere, it's getting lower and lower. Because inversion through a sphere pulls it, if you're outside the sphere, then it pulls you inside the sphere, and pulling inside a sphere is bringing you closer to the center of the sphere, but the center of the sphere is in the plane.
Yeah.
So the only limit points of this orbit will be on the ground. And in fact, the limit points will exactly be the entire circle packing.
So this is a video illustration of what Alex just talked about. Here we have 4 mirrors in hyperbolic 3 space given by the hemisphere and the 3 planes. This is a slight modification of the case of 4 hemispheres, but the overall picture remains the same. Repeated iteration of these mirrors yields limit points on the boundary plane. These limit points are shown in black, and they arise as the complement of the interiors of the disk shown. These disks are those of a circle packing associated to the hyperbolic mirrors. Note that the two horizontal lines in the circle packing are to be thought of as circles of infinite radius passing through the point at infinity.
So that's a crazy thing that happens. And the fact that all of this is going on is what's underlying that theorem about the number of points. This counting theorem about how many circles there are with radius at least 1 over x.
Okay.
So it's the spectral theory of hyperbolic space and flows in hyperbolic space that allow one to prove such a thing.
Wow, that is beautiful, because you would have never thought. It's one of those things where unless you make this connection, that door is just completely closed. Right?
Absolutely. Yeah. And it's very similar to I don't know if you remember like studying harmonic analysis and Fourier analysis. And if you have a function on the real line, and let's say it's smooth or something, so then the Fourier transform you can integrate by parts and show that it'll decay faster than any polynomial.
Right.
Like it'll decay like 1 over x to your favorite power.
Right.
But if you actually know that your function is not just on the real line, but it has an analytic continuation into some half plane, then you can say that the Fourier transform actually decays exponentially, not just as some polynomial. So this deformation, this like complexification of a problem is something that's a theme in mathematics. And this is one instance of it where Poincare says, you can't see what's going on because you're in the boundary. The real action is happening in the upper half space. And that's where you can, grab these techniques and do all kinds of cool stuff.
Yeah. Okay. Wow. Look, very cool stuff.
Okay. So now we're getting very close to Soddy's observation. Remember Soddy's observation? We had this formula from Descartes, B1 plus B2 plus B3. Okay. So we had this B4 and B4 prime. In our case, if the black circles are B1, B2, B3, they're the ones that we're thinking of as being fixed. And then we have the two solutions to the Apollonian equation, which I guess I'll put in yellow. The inner one, which is B4, and the outer one, which is B4 prime. Does that make sense?
Yep.
And so there's an action that replaces, where can I draw this? Well, I'll try to put it here. So if I think of the four tuple, B1, B2, B3, B4, and I want to replace that by the four tuple B1, B2, B3, B4 tilde.
Okay.
I can accomplish that by a matrix multiplication. I mean, a matrix is just a convenient way to keep track of it. I leave B1 alone, I leave B2 alone, I leave B3 alone. And in place of B4, I'm gonna use this equation. So B4 prime, if I just move the B4 to the other side, then B4 prime is 2 B1s, 2 B2s, 2 B3s, and minus 1 B4. But check this out. This matrix is the realization on the level of bends of what this circle, maybe I should have drawn it in green, it's exactly what inversion through this circle accomplishes geometrically. So there's some conjugation from the world of four tuples of bends to the world of four tuples of circles, where this S4 conjugates to this matrix. And the thing about this matrix, and this matrix is an involution. You square it, you get the identity matrix. There are three other matrices just like it, with identities in all the places except one row, and one row has a minus sign on the diagonal and twos off the diagonal. And the group generated by, so this is called the Apollonian group. The group generated by these matrices that look like this guy.
And this is a representation of the group, right? What you just wrote.
That's right. Exactly. Exactly. This group, well, just look at it. The entries are all integers. So if I have an initial configuration, which has all 4 integer bends, I'm multiplying and adding integers. All the
I
other
see.
bends are going to be integers.
So, oh, okay. So the point is this. Um, the actually, pause here for a second. So Descartes' theorem tells you that for any of these inversion groups generated to any 4 circles, right? That has a presentation, or sorry, these 4 circles with the appropriate tangent configuration.
Yes.
They have this representation, right, in terms of integer matrices. And so as soon as you have 4 integers, you will forever have 4 integers because of the fact that the coefficient matrices themselves are integral.
Absolutely. So that's a modern version of Soddy's observation.
So he understood it in his language.
Yes.
Yes. Okay.
Which is the same. I mean, if you just look at this equation and you say I get new things by taking twice a bunch of other things, adding up and subtracting something. Of course, I can't get out integers if I start at
right. Yeah, I mean, you don't need representation theory to say the minimal thing, but basically there's an integral formula that iterates, and if you just understand that, then you're good to go.
Yep.
Yeah.
Just to say one more thing on here, which maybe will take us too far afield, but as long as I have the picture of hyperbolic 3 space, I can't not say it. So, so you remember Descartes' theorem, which is that the sum of the 4 squares, so this is b1 squared plus b2 squared plus b3 squared plus b4 squared, is half the square of the sum. So if I multiply by 2 to get rid of that half, and I subtract the square of the sum, b1 plus b4 squared, so that equals 0.
Yep.
Right. That's Descartes' theorem. Well, this is a quadratic form. Let's call it Q. Q of the vector of b's is equal to this, and Q equals 0. So what is this as a variety? So let's think about this variety, Q equals 0. So the real points, quadratic forms have signatures. Does that ring a bell? You can write this down as a matrix,
right?
So the Hessian matrix, and it'll have eigenvalues. Some number of them are positive and some are negative.
Right.
Can you guess what the signature of this quadratic form is? How many positive eigenvalues? How many negative eigenvalues?
Well, I'm staring at the S. Is it what, 3 positive, 1 negative?
That's exactly right.
Okay.
Which is why we have hyperbolic 3 space.
Okay. Yeah.
So this cone, Q equals 0. So Q equals 0 will be some Minkowski space, some cone, right? Q equals 0. Q equals 0 is a cone in R3 plus 1 space. So if I think of this of this Q as an inner product, then if I pull just off of Q equals 0 onto something like Q is positive, right here is a model of hyperbolic 3 space.
Okay.
And a projectivized okay, now I'm really going to get a little too far, but
that's fine. That's fine.
The boundary Q equals 0 is exactly this boundary at infinity of this ideal boundary of hyperbolic 3 space. So there's at least some hints there of what's really going on.
I'm trying to think. Sorry. So, so you said a model of hyperbolic space is restricting this Minkowski metric to this upper hyperboloid. Is that correct?
Exactly. Yeah. So
now
one sheet of the 2-sheeted hyperboloid.
Right. And so that corresponds to the open upper half space. And you're saying that there's a way to sort of match the two compactifications, or maybe not, or completions. Rather. In the upper half space, you're just going to add the half space itself, the
this
R2
boundary. Yeah. Yep.
And then
R2. Yep.
Right. And in the Minkowski space model, you're adding the cone somehow.
Yes, exactly. Okay. Yeah. Okay. And the cone itself is too much because these points will all be the same. It's really the directions of the cone. So it's the projectivized cone.
Okay. Okay. Because I was going to say, one thing that was disturbing me about this picture was that this might just be a visual artifact, but in the upper half space picture, the R2 is like literally the boundary,
Yes.
right, of the upper half space, whereas that's not the case with the cone. So that was kind of messing with my
Yeah.
my
So what's
eyeballs a little
happening
bit.
here
Yeah.
is that this hyperboloid gets closer and closer to the cone as it comes farther
Ah,
out.
now that makes okay. That's why you said okay. Now that makes a lot more sense. Okay,
Yeah. And so you can
yeah,
just start to think of this boundary at infinity.
got it. Okay, this makes sense. Okay, yeah.
And so what's really going on is that this four tuple, B1 through B4, is a point on the cone by Descartes.
Okay,
Descartes' theorem
yeah.
says that the
Okay.
quadratic form applied to that four tuple is 0.
Yep.
That's a point on the cone. And then this matrix group is a subgroup of the orthogonal group. It preserves the quadratic form.
Yep.
So this gamma sits inside the orthogonal group, preserving the quadratic form. And of course, it has integer coefficients. So it sits inside this OQZ. And the orbit is some orbit of four tuples staying on the light cone on Q equals 0. Great. So then what? Well, now we have all these whole numbers, and they're kind of funny. They're kind of interesting. We had what was it? A 2, a 3, and a 1. And then there was this 23 inside. And then you'll get more whole numbers inside. And then there's this minus whatever it was on the outside. I don't even remember anymore. Or this was minus a 6. 1. This was a 6. There's a minus 1 on the outside. Okay. Yeah. In fact, what's really going on here is that if you take a unit circle and you cut out 2 circles of radius a half inside of it. So if the radius is a half, the bend is 2. And the outermost has bend 1. So this minus 1 can do double duty. It turns out that the circle that fits in here has radius a third. So bend 3. And it turns out that the circle that fits in here has radius a sixth. And so there's our 2, 3, 6. The same 2, 3, 6 that comes from a 3, 4, 5 right triangle is sitting right here inside this configuration. What we worked out is the 23 that turns out to be here, 23. Okay, so that's the piece of this packing that we're playing with. Now, do you actually do you have a picture of one of those packings with the integers filled in? So check this out. Where's my pen? There it is. So we get all these weird numbers in here, right? So this is the set of bends for this packing, for this P, which is a different P. For this P, the set of bends is, well, there's the outermost. I don't remember what it is. It's minus something, minus.
Okay, we can look it up later, and I'll just paste
let's
it.
just pretend it's minus 11. I don't know if that's right or not. Then there, I see an 18. I see a 23. I see a 27. I see a 35. What else do I see? A 62, right? 63. You see what I'm I'm just sort of finding the next number that I can. I see a 63. Like, is there any rhyme or reason to these numbers?
Not from what I can see with my naive eye.
Yeah, it's hard to tell, right? So for example, there's a 135 here, and there's another 135 right there.
That's kind of a curious thing, right? It has multiplicity too.
Yeah, and there'll be more numbers. So here's a 242 and another 242. So in fact, if you think about it, there have to be multiplicities, at least eventually. Because if we look at how many bends there are, the number of bends that we'll see with multiplicity, the number of bends with multiplicity up to x. That's exactly how many circles there are with radius at least 1 over x.
Yep.
Right? This is the number of circles in the packing with radius at least 1 over x. But that's exactly what we know what that is. It's some constant times x to the 1.3, roughly. And 1.3 is bigger than 1. And so we have no other choice but to see multiplicities. Does that make sense?
Yep. Yep.
So it turns out there's this crazy series of papers by Graham, the now late Ron Graham, Graham, Ligarius, Mallows, Wilkes, and Nguyen. So there's from about 20 years ago, I think starting in 02-ish. And there's a long series of papers where they try to understand some pattern in these numbers. You know, what can we say about them? And one of the first things they observed is that there are only certain residue classes, mod 24, that are represented.
Mm.
So the B's, if you look at these B's, so their observation, if you look at the B's mod 24, you do not get all the numbers mod 24. So I see 23, I see an 18. What's 35 mod 24? 11, I guess.
Mm-hmm.
And then, I mean, there's a couple of residues, but then there are a bunch that are missing. And then what they notice is if you go far enough out, it looks like what happens is every number that's in one of these residues, mod 24, occurs. And that seems to be the conjecture.
Okay. Actually, just back up.
Yeah.
Where did 24 come from?
Okay. So 24 for them came experimentally.
Oh, okay.
But we now know where 24 comes from. It comes from that group. So if you look at this group again, now we're really going to get into the weeds because now we have to talk about strong approximation and of semi-simple groups. So we had this group which was generated by these matrices, right?
Mm-hmm.
These four matrices, and we said that this group is a subgroup of the orthogonal group preserving this quadratic form with integer entries. Mm-hmm. Again, maybe I'm getting too far out.
I'll stop you if you are.
Yeah. So if you look at the cone, if you look at q equals 0, our variety, but now instead of looking at the real numbers or the integers, if you look at z, over finite fields, fp. So this is like the adelic point of view. Is there are these other completions of the rationals. There's the Archimedean completion and the p-adic completions. And if you study all of them together, that'll tell you something about solutions to equations, especially for quadratic forms, where we have something called the Hasse principle.
I see. Yeah, this is definitely way deep because I didn't take any number theory, but okay. I mean, it's okay.
So that's perfectly fine. Nothing that I'm going to say is too. It'll come back down to earth in a second.
Okay.
So the point is, when you take the reduction mod p of this weird group gamma, right? I don't know what elements of the orthogonal group. The orthogonal group is an algebraic group. Well, it's an arithmetic group. It's the integer points of an algebraic group. What does that mean? Q. How far do I want to get into this? OQ is defined by polynomial equations.
Okay.
Yep. And so now I'm taking the integer points of this polynomial equation. So it's very easy to tell when I'm in OQ. I just check if I write down some matrix, is it an OQ? Well, I just check if the entries are integers, and then I check if it preserves the quadratic form. And if it does, then that's the definition. But if I give you that same matrix and I say, is it in gamma? Is it in this gamma?
Mm-hmm.
I don't know how to tell if it's in gamma without trying to write it as a word in the generators. So it's a completely different, even the membership problem is completely different in this group as opposed to this group, which is the beauty of arithmetic groups. They're defined by polynomials. But the theory of strong approximation tells you that when you reduce this weird group mod p for almost all primes p, you'll get the full reduction. That you'll get exactly the same thing as you would get if you reduced this thing mod p.
Oh wow! Wait, so hold on, let's back up. So the group gamma is much smaller, or whatever. It's smaller than the integral points of OQ, but you're saying that for most primes p, that they actually collapse to the same thing when you reduce.
Exactly. That's the strong approximation phenomenon. The index of this group, gamma, has infinite index inside
Okay.
this. So it's
Okay. Okay.
absolutely much, much smaller.
Okay. Okay. Yeah. Yeah. Okay. That's what I meant by small. Yeah. Okay. So
Well,
so so that index depends on your characteristic, and you're saying basically that index becomes one for many primes p.
that's right. So instead of, I mean, the index is an index on groups. I'm changing the groups, right? I'm looking at OQ not over Z, but over the finite field FP or
Oh, sorry.
something.
Oh, sorry. Yeah. You're not reducing. Yeah. You're changing the field itself. Yeah.
But
Okay.
you should think of it as reducing. I mean, that's
Oh, okay.
this scheme version
I see. Okay.
of
Okay. I'm clearly just being ignorant, but okay. Yeah. Okay. Go ahead. Yeah. Okay.
no,
Mhm.
you're actually
Yeah.
you're saying exactly the right things.
Oh, okay. Okay.
I mean,
Okay.
the ideas are in the right direction. Exactly right.
Okay. Okay. Okay.
So I do think of it as reducing both things mod p, but when I reduce mod p, when I reduce the structures mod p, I get different groups. So now I have one, so I get finite groups. So the index is automatically going from infinite to finite when I reduce mod p. But what's striking is that in fact they're the same group for all primes. It turns out in this case, so that's a general theory. The strong approximation of Zariski dense groups is a general theory, whatever all those words mean. But in this case, it turns out that the point at the primes for which this fails to hold, the only primes for which you don't get everything when you reduce mod the prime, are 2 and 3.
Okay.
And
Okay.
then so the p-adic structure is that you don't want to just reduce mod the prime, but mod prime powers.
Okay.
And at a certain point, when you reduce mod a high enough power of your prime, then what you see in the new modulus is whatever you could have seen in the new modulus on the other group. I realize I'm saying this in a kind of I'm trying to avoid the jargon.
I see. But it sounds like basically if you push further on these ideas, this is how, I mean, my original question is how does 24 come up? So 24 is something special relating to these sorts of reductions or things like that, right?
So 24 is 3 times 8, and 8 is 2 cubed. So 2 and 3 are the only primes that cause trouble. 3, once you look mod 3, then mod any higher power, you get the same thing as just whatever the deficiency is in the group mod P being, or mod Q being the orthogonal group, mod P to the n. If you take your group gamma, let me try to say this again. You take your group gamma and you reduce it mod P to the n. You, for almost all primes, will get everything that you would get if you took this and reduced it mod P to the n. The primes for which that fails is 3 and 2. And if you look at the towers above 3, so 3, 3 squared, 3 cubed, and so on, you immediately, when you pull whatever the deficiency was mod 3, you can't avoid that deficiency mod 9, but everything else that could be there is there.
Okay.
And mod 2, it's deficient. Mod 4, it's even more deficient. Mod 8, it's still more deficient. But then mod 16, 32, and all higher powers of 2, it's only as deficient as it is mod 8.
Okay.
So 3 and 8 are the only deficiencies, and 3 times 8 is 24.
Okay.
So 24, there's a deep reason for why.
I see. It's like the maximal deficiency, if I understand what you just said.
That's exactly right.
Okay. By maximal deficiency, it's basically the largest finite index
where we don't get transitivity. So the orthogonal group acts transitively on the cone. It moves all the points around, which means what doesn't matter what points you started with, you'll get to all the other points.
Okay.
Except mod 2, you don't get to all the other points. There's some residues mod 2 that you're going to miss. And mod 4, you're going to miss some residues. And mod 8, you're going to miss some residues. But the residues you missed mod 16 are the same ones that you missed mod 8.
Right. Yeah.
Just patterned out by 16.
Yep.
And so that's exactly what's responsible for this modular behavior.
Okay. Cool.
Okay. Cool. So here's the conjecture, and this is still a conjecture. This is still wide open conjecture. This is sort of the biggest problem in this business.
Okay.
This is like the major conjecture. It says that so you fix one of these integer packings, fix an integer packing, integral packing, and so it comes with some admissible set, some residues. There's some some list of numbers like this modulo 24. And the 24 is universal. It doesn't depend on the packing because it depends on the group, and the group is universal. Just like the Hausdorff dimension is universal.
Yep.
Okay. So you fix an integral P.
So the integral, so P only depends on the seed B vector, right?
Exactly.
Okay.
Yep. It only depends on the seed B vector, and as a result of that seed B vector, we get this set, let's call it A, of admissible residue classes.
Okay.
You fix an integral P, and the conjecture is then every sufficiently large integer, which mod 24 is in your set of admissible residues, every sufficiently large n occurs in the set of bends for this packing.
I see. So admissible I see. So admissible tells you what's excluded, but it doesn't guarantee you what's included. The conjecture is to fill that gap. It's actually comprehensive. It tells you what's in and out completely.
Exactly. Okay. So it sort of restores, from the point of view of quadratic forms. You see, this is like what Hasse worked out. The theory of quadratic forms has this local to global principle. So you have a localization. So Q is called a global field, Q being the rational numbers. And then you have ways of taking limits of Q with respect to different absolute values. There's a beautiful theorem called Ostrowski's theorem that says the only possible absolute values on Q are equivalent to the standard absolute value, the Archimedean one, and the p-adic ones.
Interesting enough, this actually came up in my previous podcast. Anyways, in a very funny way, because we were talking about my most recent guest, Greg Yang. We were talking about taking large n limits of neural networks, and he used this analogy of different completions of the fields of the rational numbers. And so anyways, so this actually came up. Anyways, so
great.
Continue. It's like math is universal. Yeah.
Math is universal. Absolutely.
Yep.
So for quadratic forms, if you're trying to solve a quadratic form, equals some number, if that number is represented in all of the completions, in other words, over the reals and over the QPs, then it's represented over Q.
Sorry, so say that again.
So this is the local to global principle. Mm-hmm. If you're trying to solve an equation like x squared plus y squared equals -1, mm-hmm. you will never be able to solve that in the rationals because in the reals, x squared plus y squared equals -1 has no solutions. So that's a failure at the infinite prime. The infinite prime being the real Archimedean value. Okay. If you're trying to solve x squared plus y squared equals 3 in the rational numbers, mod 4, there are no solutions to x squared plus y squared equals 3. If you had a rational solution, it would give you a solution mod 4. So mod 4, the two numbers, this goes back to Fermat. What numbers are sums of two squares? Mm-hmm. And primes that are 3 mod 4 are never sums of two squares. So this is the kind of thing that the theory of quadratic forms, rational quadratic forms, has been worked out for a century now. And it's basically this local to global principle that says if you know what's going on mod P for every prime P and for prime powers, you should be able to combine that information to tell you what's going on over Q or over Z.
Oh, I see. Okay.
So that's this beautiful long theory. And that theory rests very much on the fact that we understand quite well things like these orthogonal groups. So in a sense, this conjecture is meant to restore the local to global principle, but not for orthogonal groups, but for these weird thin groups. Groups that are infinite, that have infinite index in this arithmetic group.
I see.
Nevertheless, there should be something that says if you pass all the local obstructions, and local obstructions are right here in this admissibility condition. So this is called the local global conjecture.
I see.
Okay.
Beautiful.
So that's this very basic, very, very simple conjecture. Let me tell you before we leave this slide while we still have this on. Sure. Let me tell you what the best thing that we know towards it is.
Yeah, I should say I'm glad we talked about this, because when I was sort of getting a preview of this on my own, this not being my field, I couldn't appreciate how ubiquitous the ideas or the motivating principles were. And now that you flesh it out, it's like this is there's a very deep and natural continuation from older ideas.
Absolutely. Absolutely. And kind of what I love about the subject is it's older ideas from all of these other fields.
Right. Spanning millennia.
Spanning millennia. Yeah. So here's what we know. The best we currently know is the following theorem. It's true for almost all numbers. So if you look at how many numbers there are in the Bend set up to x, and you think about how many numbers there should be. So the number of admissible numbers, let's see, so n up to x, so that n mod 24 is in the admissible set. Okay, does this make sense?
Yeah, can you say in words again what the numerator and denominator are?
Yeah, so the numerator is how many numbers actually occur up to x. The conjecture is once you get sufficiently large, once you're sufficiently far out, every admissible number occurs. So the denominator is how many admissible numbers are there up to x. So this is like let's say there are 6 admissible numbers mod 24. Yeah. So then this is a quarter x.
Yeah. I see.
So the denominator is something very simple.
Basically, I think the theorem is that this is going to like approach 1 or something. If I'm reading this correctly. Okay. That's
exactly right.
Yeah. So it's basically the conjecture is asymptotically true. You just don't know if it's true on the nose.
That's right. That's exactly right. And so this is due to Bergan and myself.
Oh, okay.
So that's kind of I've sort of summarized where things stood 5 years ago, maybe a little bit 8 years ago. There's a whole other side to this story, which is what's happened since then. Okay, so let's wrap it up. I'll tell you one more theorem. We won't go into the whole other viewpoint on what Coxeter has to do with all of this stuff. That's sort of what the more modern thing is. But I'll tell you one more theorem, and that can be the wrap up. How's that?
Okay, sure. I'm just curious. Were we going to discuss anything about Escher, or is that just that's not going to be relevant anymore?
So what's really going on is that these reflections, especially when you go to the hyperbolic 3-space picture, and you have these geodesic hemispheres, these domes, and you're inverting through those domes. Those domes are mirrors in hyperbolic 3-space. And configurations of mirrors in hyperbolic space is something that Coxeter and Escher were very, I mean, they had this correspondence. And you can understand Escher's work through the viewpoint of these things. And circle packings are actually a very natural extension of these ideas of Escher and Coxeter. Okay. But to do that justice would take maybe another hour. Let me tell you one more theorem. Okay. And then because you so there is an instance where we can solve the full conjecture. Okay. But it's not in dimension 2. It's in dimension 3. So this is from Soddy's paper. He took a picture of this. You see this construction with the ball bearings. I mean, he literally constructed this thing, and that's presumably why he was the first to realize this integrality, which, like, Descartes missed the integrality, obviously Apollonius missed the integrality, Leibniz missed the integrality, like all these fancy guys. I'm sure they would have loved to know that fact. That's just a gorgeous fact, and they all missed it. But Soddy built this thing, and it forced him to see it. So here's an image of what the inside of one of these things would look like. And the labeling is, again, the bend. So this is a sphere of radius 1/28, a sphere of radius 1/81, a sphere of radius 1/85. There's the same analog of the Apollonian theorem that, remember, we had 3 tangent circles. Let me draw this again. The way that we had 3 tangent circles before, 3 tangent circles, and then there were 2 ways to put in a 4th tangent circle, right? One on the inside, one on the outside. So the same thing's happening here. We have 4 tangent spheres. And then there's exactly 2 ways to put further tangent spheres inside of them.
And I guess you need four, because a circle is determined by 3 points, and I guess a sphere is determined by 4 points, right? That's why you need. Okay.
Exactly. And what you did in order to prove that, in order to construct things, was you moved it to this configuration.
Yep.
By a transformation, and then it was sort of obvious that there were two, one on this side and one on that side.
I see. And figure C is the analog of that.
Exactly right.
Yeah.
So here's one of the spheres has been turned into a plane. Another of the spheres have been turned into a plane. Two of the spheres are tangent spheres. And so where are you going to put the other ones? It's sort of obvious. You're going to pack them like ball bearings. Okay. And then if you continue adding more and more spheres, that's exactly what in the limit becomes this object. And in this setting, so here the bends, it turns out that the only prime that you have to worry about is 3. And it turns out that the bends are either 0 or 1. For this particular guy, the bends are either 0 or 1 mod 3. So that's the admissible set. So you see 27 is one more. 27 is a multiple of 3. 28 is one more.
I see.
81 is a multiple of 3.
Yeah. The prime you have to worry about is absolute across all packings, but the particular admissible bends depend on the initial seed.
That's right.
Right. Okay.
And the only options are 0 and 1 or 0 and 2.
Oh, okay.
It turns out.
Okay.
And in this case, you can actually prove the full local global theorem. So the theorem says that given one of these sphere packings, for a sphere packing, I call these Soddy sphere packings, Soddy. For a Soddy sphere packing P, every sufficiently large n, which mod 3 is in the admissible set. So this is our admissible set in this case. N is in the bend set. So this is my theorem from a couple of years ago. So so we can prove the full local global if we go up a dimension.
Wow, that's beautiful.
So, well, then the question became, what are the other types of configurations? Like we have these sphere packings in dimension 3, we have the circle packings in dimension 2. Is there more to this story? Why do these things exist? Well, so the answer to why these things exist is that other half of the conversation. They come from these reflective groups in hyperbolic space that start with the Coxeter-Escher story. So maybe we'll talk about it another time.
Sure. Okay. Well, wow, this was great. You must have been really happy when you proved this theorem, I suppose. I don't know how long were you working on it?
This theorem, I do like this theorem a lot, of course, but it's actually much easier than the one with Bergan, which gets nowhere near as far. You see, in higher dimensions, you have a lot more points to play with. And so it was still quite a bit of work, but it wasn't anywhere near as difficult as the other one.
Okay. All right.
So, sometimes you like the results, sometimes you like the proof.
Okay.
I like the proof of the other one. It really uses sort of everything. It uses basically all the mathematics that I had learned up to that point in my life, all went into one theorem.
Awesome. Great. Well, thank you so much, Alex. This is definitely the first of my podcast episodes where we really went into a topic that was outside of my education, so to speak, and I'm glad I did it because I learned a lot of stuff that I wouldn't have learned otherwise.
Yeah, my pleasure. I mean, I do hope you feel like, I did tell you don't prepare, but I hope you see that like these kinds of things, there's no reason small children can't understand these things and play with them and experience math in a way that, lets them access deep things that are low hanging.
The funny thing, I was going to say it earlier, but then I didn't want to interrupt. But you mentioned how you liked math in terms of like examples, essentially. And I was going to say, that's like very much the Russian way of doing things, right? Like the opposite way is the Bourbaki. So you must hate Bourbaki, right?
I hate Bourbaki. We'll have a whole conversation about Bourbaki.
Okay.
It's funny because now that I'm doing more stuff with formalization, I'm a little bit getting more respect for Bourbaki than I had before then. But
Yeah, yeah, because it's if you want to formalize things, the dry and cut algebraic way is straightforward, whereas the loosey goosey Russian intuition way is going to be a little bit harder, right?
that's right. But the way that I understand things is that intuitive way.
hmm hmm
But I still appreciate being able to write things down, extremely precisely, and I see the value in it.
Mm, great. Well, thank you so much, Alex. This is a lot of fun.
My pleasure. Yeah, nice to chat with you.